So we have seen what hyperbolic geometry is in terms of what distances are. Now let's try to see what are the straight lines or the natural substitutes for straight lines. So first of all, what are Euclidean straight lines? Well, they have the following property. Let's take a straight line and take 2 points P and Q on it. Well, let's call this L. So the shortest path between P and Q lies on L. Okay, so this is the property that you would want to abstract out, and in general, gamma contained in X satisfying this is called a geodesic. Now I should point out here, satisfying this, well, or somewhat weaker conditions. Now in hyperbolic space, as with Euclidean space, the weaker and the stronger conditions say the same thing. Okay. So I won't emphasize this, but let me just say a couple of things. Firstly, you might want this to be true only locally. That is, not for every pair of points is the path, shortest path joining them actually on L. Okay. So here we took P and Q arbitrary, but if P and Q are sufficiently close, that is to say, gamma will have to be covered by intervals on which this property is true. So that would be one change that you could make to the definition. And in the second change you could make to the definition is, I said, it in the shortest path, that is to say the unique shortest path. Of course, the shortest path may not be unique in general. You would replace the by a shortest path. So these two changes will allow you to define geodesics. Depending on the context, you may want to make one or both of these changes. So our goal here is to determine hyperbolic geodesics. Okay, this is of course standard Riemannian geometry, but we won't do that. What we'll do is use a lot of symmetries. So our first set of hyperbolic geodesics are vertical lines. So here we are looking at the upper half plane, and let's take a vertical line. Okay, perhaps it will be in another color. Okay, let's take a pair of points on it, P and Q, and we claim that the shortest path between P and Q actually lies on the line which I haven't yet given a name. Let's call it gamma. Okay, so here's the proposition. The shortest path between P and Q, so PQ and gamma, lies in gamma. And the proof is actually very simple. And the proof is that if given any path, let me call this something alpha from P to Q, projecting onto the line, onto gamma, shortens it. Now shortens it, I mean in the weak sense, that is, if it was already on the line, it does not actually shorten it, strictly speaking, it keeps it the same length. Okay, so let's project it this way. What happens? Why? Well, there are 2 points to note. One is that Euclidean length decreases. This is the case for projections always. That is to say, if I'm looking at a tangent vector like this, it's become a tangent vector here. which has become shorter. Projection always decreases length. Okay. Strictly decreases unless it's already in the projected space, in which case it keeps the length the same. But hyperbolic length is not Euclidean length. However, remember that the hyperbolic length, okay, I've written it like this, it's 1 over y times dh, the Euclidean. What this notation means, I've sort of changed the notation, but the key point to note is that you have a scaling factor. So let me revert to better notation. The hyperbolic norm is 1 over y times the Euclidean norm. The scaling factor is unchanged. This is because we projected onto a vertical line, and so is unchanged. Well, this is because it's independent of x. Okay. So thus we have a bunch of geodesics. So thus vertical lines are geodesics. Okay. So we have identified a bunch of geodesics. This is our start of our quest. Vertical lines are geodesics. Okay, but note we use 2 points in the argument. One, projection decreases Euclidean length, and second, the manner in which we are projecting, each point is moved to another point at the same height. So the scaling factor is not changed. Okay, so if I look at a horizontal line instead, okay, which was like this, for example, or any other line with any slope, and took the same picture, that is to say I had a line like this joining it, and I projected it down. Okay, so here this is not true. Well, why not? What has happened in this case is, well, certainly the Euclidean length has decreased. It always decreases when we project. But on the other hand, the scaling factor has actually changed. That is, a point which was higher, it's come down, and this has actually increased 1 over y. And how these two interact with each other is complicated, and we won't try to understand this. Okay, instead we'll proceed by symmetries. But I made this argument to point out this works for vertical lines and not for general lines. In fact, vertical lines are the only geodesic lines, as we'll see. Okay, so now to move on to the symmetries. This is what we'll use, but in specifically we'll use symmetries and circles. Okay, so, well, let's just look at this. Lines and circles in C are given by, well, as frequently happens in geometry, circles by themselves don't form a nice set. In some sense, they're an open set. You have to include lines in them. Lines are a form of degenerate circles. Now, lines and circles are all given by an equation of the following form: P times ZZ bar plus some Z times Z plus Z bar times Z bar plus Q equals 0, where P and Q are real, and Z is a complex number. Okay. Now this quantity is a real quantity. Okay, so this is a real number, and this quantity is of course mod Z squared. In fact, this quantity is just maybe twice the real part of Z times Z. Okay. So this is a nice way of putting the equations. It's a simple exercise to see the usual way of writing the equations of circles. This will be convenient to us, okay, because from this it follows that the set of lines of circles and lines, now onwards I'll just call lines as circles usually, is preserved by Z goes to alpha Z. Okay, if you plug it in here, you'll see what happens to the terms. They all give you terms of the other form. Using the lower representation, this is easier. Also, Z goes to Z plus beta, and Most interestingly, z goes to 1 over z. Okay, so even this preserves it, because you see these two terms get flipped in that case. When z goes to 1 over z, the q term and the p term kind of get flipped when you clean out the equation. By the way, these equations may give you empty sets and so on. So I'm not saying this always gives you a non-empty circle, but you'll get all the circles, and it's easy to see what happens there. So z goes to 1 over z. Okay, that intersects, changes these terms. Hence, by all maps, all, well, bijections at any rate of this form, z goes to alpha z plus beta by gamma z plus delta. Okay, and this is the key point, that whatever bijection we have used two such bijections. One of them were az plus b by cz plus d, and the other was the one that related the upper half plane to the unit disk. Okay, and now let me just observe one more fact. These here also preserve angles. Okay, this is because any holomorphic function preserves angles. That's a characterizing property of being holomorphic. Okay, so we have something in hand. Okay, namely, we have found a bunch of symmetries and seen how they act on lines and circles. So we can find more hyperbolic geodesics. Okay, based on this following very simple principle. Let me say this once explicitly. Namely, if whatever phi is an isometry, say upper half plane to upper half plane is an isometry, then gamma is a geodesic if and only if phi of gamma is a geodesic. And so we have a bunch of geodesics. So if you want to check something else as a geodesic, if we can map it to a vertical line, it's a geodesic. And conversely, if we take a vertical line and map it, okay, so under this transformation, we get a geodesic. Okay, so let's do that. So we are applying whatever phi of z of this form, az plus b by cz plus d, to vertical lines. We get geodesics. Well, what happens? This is not the whole of the vertical line, right? It's half of it. So we have the upper half plane like this, and we have the geodesic part, which is the top part. It extends below something else. Okay. Well, we get geodesics. Well, what do they look like? They are of the form C intersection H, C circle, or line, of course, in general. But we also know something else about it. What we know, upper half plane, C is orthogonal to H. The argument I've said is not quite complete, but it's easy to just replace the completion by calculation. Okay, to complete it by calculation, the point here is simply that this angle which the circle makes with the horizontal line is the same as the angle that the vertical line makes with the real line. So that's 90 degrees. Of course, one of these angles is mapped to infinity, so this argument by itself is not complete, but it's easy to complete it. Okay, so we know that here the red one is a geodesic. Okay, so conclusion. So from this, what we can conclude is exactly that geodesics are arcs of circles, and here circles includes lines or lines intersecting are orthogonally. Okay, couple of points here. A line intersecting R orthogonally is of course exactly a vertical line. A circle intersecting R orthogonally actually has its center contained in R. For a certain reason, I'm not putting it that way, but it's useful to remember this, that you could think of these either as alternatively as vertical lines and semicircles with center being on R. Okay. So this is the collection, but for many reasons we would also want to look at the unit disk. Okay, and remember what we have is H goes to D. Okay, this is H and this is D, and we have a fractional linear transformation, something of this form, Z minus I by Z plus I. Z goes to this. This is the map which takes it. Okay, I give this guy a name. Let's call this better to have a notation here, Psi or something. Psi preserves circles, and here by circles I always mean circles and lines, and is an angles. So what does this mean? Hence, geodesics. Oh, I should state one more fact for completeness. Okay, C takes R, or more accurately R union one point at infinity to boundary of this disk. Okay, so the boundary of the disk, and that's the reason why I wanted to turn to the unit disk, because this guy is going to be boundary of H in some sense, but we have one special point while boundary of D is a nice and symmetric circle. So C takes this to this. So what do we conclude from these two facts? So thus, okay, geodesics in D are arcs of circles intersecting boundary D orthogonally. Let me draw a couple of pictures of these. So I have the circle here, and here are a couple of arcs, right? So one of them could be like this, and it intersects here in right angles. But there's another possibility, which is simply diameters. These are lines rather than circles, but lines are circles as far as we are concerned. They're lines passing through the center. Other chords are not geodesics. Now you may be wondering about one question, which is how do we know these are all of them? I just took some and then took their images and got others. Well, given any pair of points, there can be at most one geodesic through them. And it's easy to see in both, maybe even easier in the hyperbolic disk model, that there is one in our collection which passes through any pair of points. Okay, so that tells you that these are all of them, because we have got plenty and we can't have more, because of otherwise we would have two geodesics through a given line, and both of them are strict minima, remember. Okay, so finally let me just go back to the historical roots of hyperbolic geometry. Okay, so parallel postulate, well, this is violated. This is a picture to keep in mind though. So let's take a big unit disk here, and let's take a straight line. This is a straight line, and let's take a point that's not on the straight line. Well, what does a parallel postulate say? There's a unique line which is parallel in the sense of not intersecting it, which passes through this point. Well, here's a line. Okay, line in the sense of a geodesic. It passes through this point and it is not parallel to it. Here's another. And there are plenty of them. Okay, so hyperbolic means actually moving away, and the point here is that given a point line and a point on it, there are infinitely many lines passing through that point which don't intersect the given line, which is what is classically called parallel. So this tells us what the straight lines are, how we work with them, and it shows in all other axioms are satisfied, of all the other Euclid's axioms are satisfied. So historically the importance of hyperbolic geometry was that it showed parallel postulate is logically independent of the others, because others are satisfied and the parallel postulate is violated.